Welcome to our video on Kolbe electrolysis, a classic method in organic chemistry for preparing symmetrical alkanes. Kolbe electrolysis is a decarboxylative coupling reaction that uses electrical current to convert carboxylic acid salts into symmetrical alkanes. The process starts with the oxidation of carboxylate ions at the anode, followed by decarboxylation and radical coupling, ultimately forming a new carbon-carbon bond. Let's first look at the experimental setup for Kolbe electrolysis. We need a solution containing the sodium or potassium salt of a carboxylic acid in water or alcohol. The electrodes are typically made of inert materials like platinum or carbon. When direct current is passed through this solution, the reaction begins. Now, let's focus on the key chemical transformations that occur at the anode. Step 1. The carboxylate ion is oxidized, losing an electron to form a carboxylate radical. Step 2. This radical spontaneously undergoes decarboxylation, releasing carbon dioxide gas and forming an alkyl radical. Step 3. Two alkyl radicals couple together near the electrode to form our desired symmetrical alkane. The overall anodic reaction combines these steps, showing how two carboxylate ions are converted to one alkane molecule plus two carbon dioxide molecules, with the release of two electrons. Let's visualize the electron flow and molecular transformations during the Kolbe electrolysis process. The carboxylate ion approaches the anode. At the anode, it loses an electron, forming a carboxylate radical. This radical is unstable and rapidly decomposes, releasing carbon dioxide. The resulting alkyl radical is highly reactive. When two such radicals meet near the anode surface, they combine to form the symmetrical alkane product. Meanwhile, at the cathode, a complementary reduction process occurs. Typically, water or the alcohol solvent is reduced to produce hydrogen gas. This can be represented by the equation. Two water molecules plus two electrons yield hydrogen gas and two hydroxide ions. While this reaction is necessary to complete the electrical circuit, it doesn't directly participate in the formation of our alkane product. When we combine both the anode and cathode reactions, we get the overall process for Kolbe electrolysis. Two molecules of carboxylic acid, in the presence of a base and under electrolysis, yield one molecule of symmetrical alkane, two molecules of carbon dioxide, and one molecule of hydrogen gas. This is a powerful carbon-carbon bond-forming reaction that occurs under relatively mild conditions. Let's look at a specific example, the preparation of ethane from sodium acetate. We start with sodium acetate, which provides the acetate ions for our reaction. At the anode, these acetate ions are oxidized to acetate radicals, which decarboxylate to methyl radicals. Two methyl radicals then couple to form ethane. The overall equation shows that two acetate ions yield one ethane molecule, two carbon dioxide molecules, and two electrons. Finally, let's discuss some important features and limitations of the Kolbe electrolysis. First, this reaction primarily forms symmetrical alkanes, where both alkyl groups are identical. Second, yields can be reduced if the alkyl radicals undergo side reactions, such as hydrogen abstraction from the solvent. Third, the method is not well suited for forming long unbranched chains, as competing reactions become more problematic. Despite these limitations, Kolbe electrolysis remains a valuable tool for preparing specific types of symmetrical alkanes under mild conditions, using a process that forms carbon-carbon bonds through an elegant electrochemical mechanism.